Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on November 20th, 2025, just yesterday. It introduces a generative model that can reconstruct full 3D geometry, texture, and layout of objects from a single image, and it wins human preference tests by at least a 5-to-1 margin on real-world objects and scenes. The paper is titled SAM 3D, 3DFY Anything in Images. And as we will see later, the combination of data pipeline and model design leads to some really impressive gains for 3D reconstruction in the wild. Also, the authors shared a solid GitHub repo for SAM 3D objects. You'll find the full Python implementation, pre-trained checkpoints, environment setups, and a demo script, plus Jupyter notebooks for single and multi-object reconstruction, and an example showing how to align SAM 3D objects with SAM 3D body in one scene. Over on Hugging Face, you'll find downloadable SAM 3D objects checkpoints, contact-gated access, and Python notebook examples for single or multi-object 3D reconstruction from images. Figure 1 shows what makes this approach exciting. A single photo turns into a full 3D scene made of separate, reusable objects. The top panels display two everyday photos, a cozy living room and a canal street, alongside their reconstructed 3D scenes. The middle illustrations sketch how each scene is decomposed into individual objects with their own shape and pose. Along the bottom row, the figure presents the final 3D assets, which include clean geometry and realistic texture for each object that can be rearranged or reused elsewhere. Figure 2 explains how SAM 3D actually turns a masked image into 3D shape and layout. The top row shows the geometry model, which uses image and optional point map encoders, plus a mixture of transformers block to predict voxels and object pose, so rotation, translation, and scale. The right panels illustrate that mixture of transformers and its multimodal self-attention mask, which lets shape and layout tokens share information. The bottom row then feeds coarse voxels into a separate texture and refinement model that adds mesh detail and realistic surface appearance. Figure 4 summarizes how the model learns, showing a staged training pipeline that moves from clean synthetic worlds to messy natural photos. The top row traces model training blocks, from synthetic pre-training through semi-synthetic mid-training and real-world fine-tuning to preference optimization that directly uses human choices. The lower purple boxes mark raw data sources, synthetic three-dimensional meshes, and natural images, while the yellow blocks show the human and model in the loop data engine that keeps generating better supervision. So while Figure 4 sketched the training pipeline conceptually, Table 1 spells out the concrete stages and data choices that make that pipeline work. This table shows two parallel tracks, one for the geometry model and one for the texture and refinement model, each moving through pre-training, mid-training, supervised fine-tuning, and preference-based alignment. It lists which three-dimensional modalities are predicted at each step, which datasets feed that step, and whether the model sees an object-centered crop, a full image, or an optional point map, so you can see how the supervision and inputs steadily become more realistic and human-guided. Table 2 shows that this model delivers the strongest overall 3D shape reconstruction among current image to 3D methods on both real and cleaner benchmark images. The SA3DO block reports geometric accuracy, using scores like F1 at 0.01 and chamfer distance, which measure how closely the predicted surface matches the ground truth mesh. The ISO 3D block instead uses perceptual similarity between rendered results and the input photo. Across nearly every metric, SAM 3D stands at the top, so it offers both more accurate shapes and better-looking reconstructions. Table 3 shows that the joint SAM 3D model predicts object layout much more accurately than robotic-style pipeline systems on both SA3DAO and ARIA Digital Twin. The table reports measures like three-dimensional intersection over union, rotation error, and average distance difference, which together capture how well object position and orientation match ground truth. On SA3DAO, SAM 3D reaches around 0.43 intersection over union, clearly ahead of all pipelines. On ARIA Digital Twin, SAM 3D again leads with higher intersection over union and a much larger fraction of poses within the tight ADDS at 0.16s threshold, so its layouts are both precise and reliable. Wrapping up, two takeaways stand out. First, single image 3D is finally practical in messy real scenes, thanks to a smart mix of synthetic pre-training and human preference alignment. Second, the released code, models, and benchmark should catalyze new work in robotics, AR, VR, and content creation. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.